So up to this point, we I've been making these plots, putting one variable on the x and one variable on the y axes. Um, but it actually there is some choice there, and we need to examine that. And um, I mean, one thing we could say is that actually it doesn't matter, and I'll just make this clear is that the direction, form, and strength don't depend on which variable we put on the x and which we put on the y. We can flip those two variables, and if it was linear before, it's still linear. The association is still linear. If it was negative before, it's still negative association. And if it was strong or weak, that strength continues no matter if we swap the two variables, one from the x to one and one from the y axis. So in some ways it doesn't matter, but there's actually a sense that it does because we think about in statistics of predicting one variable from the next. And so um, we in fact inherit from mathematics this notion that we're predicting the y-axis, the y variable from the x. That's the standard way to look at this. Um, but another way to think about that is that we set things up so that we're going to be able to predict from the x value what the y value is going to be, or estimate, right? Estimate, um, know the x and estimate the y. Uh, and a third way to talk about this is that the y variable responds to the x variable. So we would call y the response variable, or the x variable explains the y, and so we would call the x variable the explanatory variable. Just to keep those, and those are the official terms, that's why they're highlighted in red. Response goes with y, explanatory variable goes with x, and just to keep those straight, right? Explanatory variable has the x in the word itself, and so we keep that just a little mnemonic to help you remember that. Um, and so now that we have this sort of different ways of looking at the x and the y, we actually have to make a choice when we are confronted by a particular data set. But that choice is actually not necessarily fixed. It depends on the situation. It depends on how we're thinking about the problem. So let's try some examples here. Um, I have two variables that I've collected about Major League Baseball teams. One of them is the how many runs they score on, in a season or on average per game, and another is how their box office receipts are. That is, how many tickets do they sell? And the notion is that there's sort of this that a team that has lots of runs gets is interesting to watch, and so more people will come to the baseball games. Is that the case? Well, before we decide that, we sort of want to in this example try to decide which of those two variables, the runs scored or the number of tickets sold, it should go on the x-axis and which should go on the y. So thinking about this, just the way I described it is, well, the more runs, in some sense, makes baseball more interesting, which makes more people come to the baseball games. And so I kind of am thinking that the runs scored is what explains how many people show up, right? So the response, what's responding, is the ticket sales, and what explains that response is the number of runs scored. Um, we're going to talk about this more in a second, but I am using, in some sense, causal language. That is language that sort of assumes one thing causes another. But again, the caution from earlier that this is just an association, it doesn't imply causation, might be well to keep in mind throughout this discussion. That's why, in particular, I call things not, the cause and effect. The y is the effect and x is the cause. No, the statisticians have very carefully picked out the words response and explanatory to sort of step back from that notion. Let's try another example. We're we're looking at students across the country, and we look at their SAT scores and their college grades, and the thought is, well, one thing uh, um, or another of those two, some sense, explains the other one. And so that would be the x variable, ought to be the x variable. Um, in this case, it might be pretty clear that, right, the SAT scores were taken earlier, and a college admissions counselor would be very interested in, well, how this person with this particular SAT score, how are they going to do. So, okay, so they're going to know the SAT score when they're looking to admit that student, and they want to predict how their grades are going to be. All right, so in that case, what they know is going to be the X, so that is the SAT, and what they want to predict, what they think will respond, right, is the grades. So that makes the X value, the X-axis is going to go the SAT scores, and the Y value is going to be the grades. And let's try the third one. Can we estimate a person's BMI by measuring the wrist size? And this is really nice here because that there isn't a cause and effect. Your BMI does not affect what your wrist size is, nor does your wrist size affect in any way your BMI. But there is an association between the two. When they go together. That's what we're imagining, what we're hoping. So already I'm talking about estimating the BMI. So that's what I'm guessing at by measuring the wrist size. So I'll know the wrist size. So it sounds like the wrist size is going to be the X value, right? Because that's what I'll know. That's going to be my explanatory variable, and then the BMI is going to be my response variable. So I get a relationship that way. I want to just highlight the fact that it's not fixed. These answers. There's usually a somewhat common sense approach, but it can be flipped on its head. So my favorite is height and shoe size. I want to make a plot that has the relationship between a person's height and their shoe size, but which should go on the X and which should go on the Y. And I want to suggest two different scenarios. The first being a bowling alley operator. We can imagine, for customer service purposes, the bowling alley operator wants to anticipate a person's shoe size as they come in the door of the bowling alley. They're going to come over and rent shoes, and the operator says, oh, there's some coming across, and they have some way of gauging how tall they are. Maybe a ruler attached to the side of the door, and when they see a 6-foot person coming in, they want to make a prediction about what size shoes that person has before they come over to the table, so they have that shoe ready, or a couple of shoes ready, right? So right in that description, it sounds like they will know the height, and they want to predict the shoe size. So that indicates that the response should be the shoe size, right? The thing that I'm going to make a prediction about, and the height should be the explanatory variable. So that makes a lot of sense. But to flip this on its head, let's imagine a police investigator, right? They're investigating crimes, and one of the pieces of evidence they might get is a shoe print, right? And they can measure from that shoe print what size that is, and does that give them information about how tall the suspect might be? So in this case, what they know is the shoe size, and so that becomes the explanatory variable, and what they'd like to predict is the height, so that's my response. So you notice that depending on the scenario, that can change what goes on the x-axis and what goes on the y. In most cases, it's obvious. Most cases, you probably can figure out what's going on here, but I just want to. It can depend in some cases on what context we're working in. So let's take again another real example that with real data. We're looking at the movies again, and we want to look at the association between runtime and the domestic gross, the U.S. gross receipts, how much money they received for that movie. And so, what context do we put on this? And I guess what we could say is that, that we think, well, if you have a really long movie, then moviegoers don't like the movie, and so are less likely to show up to watch it, right? And so that in that description, it sounds like I'm talking about the length of the movie, explaining how much money a movie makes. Or another way to say that, right, the opposite way is to say the receipts of that movie responds to the length of the movie. So that those things indicate that the response variable ought to be the U.S. gross, and the explanatory variable should be the runtime. And of course, what that means is that runtime goes on the x-axis, and U.S. gross goes on the y. So take a look at this plot. Here's the plot. So of course, what we want to do. I hope you're getting used to this. Every time you see the scatter plot, think direction, form, and strength. So what do we see here? Direction. It's kind of hard to tell, right? I mean, we've got some things going up here, but we also have sort of a flat part down here, right? That is, long movies can make a lot of money or a little money. But it seems the same thing is true down here. Less than 90-minute movies, they're making next to nothing, and also making quite a bit of money. So there doesn't really seem to be much pattern here. The direction may be positive, but it's not 100% clear. Nor is it clear what the form is. Be careful, because well, actually, I think in this case you could make a good argument that we've got a kind of a linear form, but there is all these other points, and so that those become difficult to fit in with that one line. So linear, maybe strength, and again, what I said earlier, short movies making lots and little, long movies making lots and little, kind of make it say that there isn't much strength. Okay, that's weak or none. So it does seem like this points to the fact that movies, it doesn't really matter how long they are. They can make a lot of money, they can make a little money, right? If they're long or short. So, but there is this interesting, phenomenon showing up. There's sort of this cluster of movies, this group here, that kind of, if I deleted those, just the bulk of the movies down here kind of are pretty clearly flat. But these up here kind of do seem to tend to be making more money the longer they are. It would be interesting to look at these movies here and figure out what they might have in common, and that there might be, this data seems to be pointing to the fact that there might be two different groups of movies as far as gross receipts are concerned, right? A third thing to note is that there is this crazy point way out here, and of course that's King Kong again. What's interesting is that it's U.S. gross receipts. Looks like a very long movie, but not earning much money. It's right there at about $50 million. It turns out that there was an error in the U.S. gross numbers as they were entered into the data set. I went back to IMDb, and it turns out that they messed up not only the budget, but also the U.S. gross, and left and dropped an extra zero at some point there. And so actually this point ought to be way up, high up here. So it would fit that pattern. I don't know how much, but it would be less of an outlier in that case.